Now let's start the fun part. Let's construct a full-fledged microprocessor which can process our CS147 DV. So processors are fully dependent on the instruction set architecture. Okay, so different processors supporting different set of instructions, different formats. All of them needs different circuitry. So our target in this lecture is to understand how from a given specification of instruction set architecture we can develop a circuit, at least logical circuit, which can act as a processor. As I was mentioning during the ALU construction that there is this data path and control path. Let's look those definitions here in this slide. Now, data signal carries the information to be processed or already processed. So it is kind of those signals, those paths along with some incoming data or information get crunched, get processed, and like maybe some in terms of some temporary information, and those temporary information gets combined, and ultimately it goes out as an output of that whole circuit. So that's the data path. Information flows through the machine. Control signal control the data flow through the circuit. Okay, so maybe some part is crunching, multiplication, or division in terms of ALU. So your controller circuit should control the information towards the right element, data processing element, so that this information can be processed. So that's the control signals and control path. So data path consists of the component which perform the arithmetic operation and store the data and the signal connection between the data. Control path consists of component which generates and route the control signal to the various part of the data path to control the flow of data. Okay, so this is the data path and control path. So each section will be discussing separately about data path and control path, but data path is mainly will be our focus, and we'll try to understand how the information being processed. Okay, control path is more like we have a controller and control signal is generated. Control signal generated at specific time. So we'll understand that, but we'll more focus on the data understanding of the data path. Data path has couple of components that being reused for different operations. One is program counter. We know its purpose is to fetch the next instruction, at least point to the next instruction to be fetched in the instruction fetch state. Stack pointer points to the stack part of the memory, instruction register, which basically store the instruction which is fetched during the instruction fetch stage. Register file, ALU, and memory, right? Those things we kind of all know what their functionality is. We have already been introduced to those components. So our target is to identify data path of the each instruction and operation using this common component, and then combine the data path using multiplexer if there is a data path conflict. So that is main principle of designing a processor. Identify your data path for each instructions and operation using common components, and combining those separate data path into one giant data path. And if there is a data path conflict, means incoming information to a component can have multiple sources, you basically place a multiplexer to select between conflicting data source. And designing controller is identify the control signal including common components, so and the multiplexer that may have been placed to arbitrate the data source conflict for a given component for different instruction and operations. So you basically identify all these control signal including those components like register file has read and write control, ALU has operation code, and multiplexer of course has a selection logic there. those things comes in, and memory, outside memory is also like have and read and write control signal. Those things comes as a set of control signal that has to be produced by your controller. Also, controller is a state machine. It cycles through these 5 states. We have already discussed those states in details in various point in our this semester. Okay, so instruction fetch, instruction decode, register fetch, execution, mem, write back, and there would be additional no operation or wait state if needed if a step is not completed within one clock cycle. Okay, so let's say we are attaching a memory which takes like more than one cycle to complete the its operation. Then during the instruction fetch and during the memory that state, we can probably have a wait into those stages. For our project and for our like both project 2 and 3, we just assume that we don't need to have any no op or wait state. We'll just cycle through these 5 IF, IDRF, EX, and MEM and WB, these 5 state always, and all the related components are done doing its operation within one clock cycle. So that's a simplistic assumption without going into this additional NOP and wait state complication. Now each state will create appropriate control signal depending on what instruction is executed. We'll talk about that in detail.